I'm Josh Tobin. I'm a research scientist at OpenAI, working kind of right at the intersection of deep learning and robotics. So a lot of my work is on using deep neural networks to learn perception models so that we can then have robots that do things in the real world. Kind of one of the main focuses of my research and my PhD is on how to actually do that with synthetic data. So how to generate data from a physics simulator or a graphics engine and then bridge the gap to make that data work in the real world. I've been working in AI for about 4 years now. I got started when I got to Berkeley as a grad student, and I was actually I'd studied pure math as an undergrad. I like to tell people I was like a philosophy major who had taken 4 semesters of calculus. Like I learned really all of the useless stuff, and I didn't know how to program. And then I went and worked for a while as a consultant, and then coming back to grad school, I knew I wanted to find some way to apply math to technology, and then just took an amazing class with my now advisor at Berkeley, Peter Abil, kind of working on deep learning and robotics, and just kind of immediately saw that this is the exciting thing to be working on right now, and I've just kind of gotten swept up in it ever since. So, in addition to the organizers, we have an amazing set of guest lecturers over the next few weeks. Peter Abil from Berkeley, kind of one of the foremost researchers in AI and robotics. Stuart Bowers from Tesla. Sergey Karyev, who built an amazing product called Gradescope that recently got acquired by Turnitin. Neil Khosla, who will be here tonight, who founded 2 AI startups. Roseanne Liu from Uber. Lee Redden from Blue River Technologies. Paroma Sharma, who kind of works on an amazing data labeling system at Stanford, and then Peter Wellender, who's one of my colleagues at OpenAI. So we're really excited to have all these great people here. I wanted to just say a few things about kind of why this class, like why are we organizing this? I think like all of you are probably familiar with lots of the successes of deep learning at this point. This chart shows image error rate before and after deep learning. There are amazing successes in games. Recently, a team at OpenAI beat the world champions at Dota 5v5, which is pretty amazing. A couple of years ago, DeepMind beat the best Go players in the world. Speech recognition kind of followed a similar trend. Before 2008 or 2009 or 2010, kind of all of the major successes had incremental progress, and then after deep learning came in, progress sort of became exponential for the next few years. Image captioning, applications in medicine, there's quite a lot. And the amazing thing about it to me is that like the amount of time between when these academic successes started coming out and when deep learning started getting used in products was just like really, really short. And so here are some products that are like actually really using deep learning right now. If you use Google Translate, then there's basically a big LSTM, or maybe they have like a more state-of-the-art model now, but a big deep learning model behind the hood. Tesla yesterday demonstrated, 2 days ago maybe, demonstrated some like pretty incredible self-driving capabilities. Their team there relies pretty heavily on deep learning for their perception stack. Speech to text is mostly deep learning based now. Photo tagging, and then up on the right, this is kind of like a press image from DeepMind's data center optimization program, where they used deep reinforcement learning to reduce cooling costs in their data centers by something like 30%. And so this is really inspirational to me, because it's like all the stuff that people at Berkeley and other places are writing papers about is really quickly making its way into the real world. But what's kind of challenging about that is that deploying deep learning systems is really different than deploying typical software systems. And so there's a bunch of reasons for that. I like this cartoon from XKCD. So it's like, this is kind of a characterization of a machine learning system, right? Like, you have this pile of data, and then you stir it around, and then eventually, like maybe some magical answer pops out, right? So the idea here is that like deep learning is like really a black box, I think, for a lot of people. But it's worse than that. Deep learning also creates a ton of technical debt. And there was a great paper about this I think from 2016 from Google, the high interest credit card of technical debt. I would highly recommend reading this at some point, because they point out a lot of ways in which building machine learning systems, while it kind of feels like cheating, you're getting the algorithm to figure out the answer for you. In reality, you're kind of accelerating the rate at which you're doing things that are not going to scale with your engineering system. And then lastly, kind of there's this idea that maybe actually deep learning is not really software engineering at all. It's actually an entirely different programming paradigm. And so this is a slide from Andrej Karpathy, who has this idea of software 2.0. And the idea is basically, in software 1.0, traditional programming, you have some goal, and then a human manually encodes some rules that help the machine solve that goal. And in AI programming, you have some abstract goal, like you have something that you want the system to be able to do. And then the way that you program the system is through data. And so the programmers in this paradigm are actually people who are collecting and labeling data sets. And then there's an optimization program that selects the best program from within program space to achieve that outcome. And so if you ascribe to this viewpoint, then you might think that deep learning programming is something entirely different than software engineering. And so I think one of the side effects of all of this kind of getting adoption in industry so fast is that a lot of the knowledge of how to do this well, right? So it's different than software engineering. It's harder in some ways and easier in some ways. But the knowledge of how to do that is kind of locked away in big companies, right? I think Google employs a huge percentage of the people who are great machine learning engineers. And in general, I think people that I've talked to at startups talk about how difficult it is to find people who have experience deploying systems like this in the real world. And then, in addition to kind of talent being concentrated, a lot of times these rules just really aren't written down. And you have to, one thing that I found really surprising when I started working in the field was, I thought that if you just read all the papers, then you could learn everything there is to know about machine learning. But that was very, very naive thing to assume. It turns out that really one of the best ways to learn this stuff is to go and talk to the people that already know how to do it, because a lot of this information is really trapped in their heads. And even once you get a handle on things, the field is still evolving so rapidly that it's often difficult to hold on to that. And I think another thing that I've heard from a lot of organizations is that a lot of these practices around how do we actually get these systems to work is kind of figured out on the fly. And so, the reason that we put together this course, in part, is to try to teach you, some of what we as practitioners know about this. So to, solve the problem of things not being written down. But I think the goal is actually bigger than that. And, hope you all have had a few minutes to chat with each other. And I think one of the great things about this class is we have a pretty amazing set of participants. And so I hope that throughout the course of the class, you get a chance to get to know each other and share knowledge and kind of just talk about the challenges that you're facing as you're learning the field or as you're actually going and deploying stuff. So just have a community of people that are all thinking about these problems. And then the last goal is really to learn by doing. So again, most of machine learning is an empirical science, and a lot of what you need to know about it, you can only kind of really figure it out by going and trying this stuff on your own. And so the way that we set up this class is it's centered around a project. And I'll talk in more detail about this later, but we're gonna have kind of 4 or 5 people per team, or actually 3 to 4 people per team. And you're gonna pick sort of an applied deep learning project and work on it together throughout the course of the class. In addition to that, we're trying out a flipped classroom style. So we have a bunch of lectures on this subject that we recorded for full stack deep learning bootcamp. And so one thing that we're going to do in this class is we're going to have you all watch the lecture videos before you come to class. And for the most part, and this class will be a bit of an exception, but for the most part, the goal is to kind of minimize the amount of time that I'm talking at you, and to spend more time listening to guest lecturers share their experience and kind of working on exercises together. I'll say a few more words about the project. We have 7 or so weeks, and so it's a pretty tight timeline to do a really good machine learning project, but it's very, very doable. And so the goal is like really to get a demo of what your system looks like end to end. We're not expecting you to like fully solve this problem. And my other goal is like I really want everyone to work on something that they're excited about. And so I've compiled a list of project ideas that I'll share with you towards the end of class. But my hope is that a lot of people have their own ideas about what would be a fun project to work on. And I would really like you to work on those ideas and maybe even convince some of your classmates to work on them with you. And then the last thing to say here, just so so it doesn't catch you by surprise at the end, but we're going to ask everyone to kind of put together a presentation about their project at the end of the class. And this is really just meant as a way of providing you like kind of a goal at the end of the class, something that you can build up to. And I think that people are going to do pretty amazing things, and so I hope it's also inspirational to see what your classmates were able to produce. Schedule for the class. This is also up on the website. But this week we're going to talk about selecting and scoping a project. Next week we're going to talk about once you have a machine learning project, you need some data, and so we're going to talk about kind of best practices for designing a data set and managing that data set. Then we're going to talk about troubleshooting. So when you're training your model, things go wrong. How do you figure out what the next step is and what to do about that? And then we're going to talk about infrastructure and test and tooling. So you're working on a larger team on this machine learning project. What does best in class infrastructure look like there? Then we'll kind of have an interlude to hear from Peter Abil about research areas. Since machine learning is moving so fast, it's more important in this field than in most fields to kind of try to stay up to date on what the latest research is, because oftentimes people will very quickly beat what you think is the state of the art on some problem, and so this will be a good way to get a sense of that. Kind of the last class week, we'll be talking about continuous integration and testing. So for those of you that are software engineers, you've probably thought a lot about this, but testing and continuous integration, there are a lot of things that are slightly different in a machine learning context, and so we'll cover that. Final week will just be the project presentations. There's a couple of things that we're going to ask you to do just to be prepared for each week. The first, as I already mentioned, is to watch a lecture video on your own before. And as you're watching, I would encourage you just to kind of write down what questions you clear. I will make time in each class to do a quick summary of the lecture and make sure that there's a chance to answer any questions. Then also, I think it's important to start making progress on your project early. And so we're going to have a mechanism for this, which is we're going to have a project updates Slack channel, which I think is already created. And we just want you to be posting updates kind of like maybe around Tuesday and by the end of day each week, just to hold yourself accountable to like making progress on the project every week. And then I'll be going through those and just giving feedback and helping you if you are stuck on anything. Cool. That's a bit about the class. Are there any questions about what we're going to cover or what this is all about? Yeah.
Slides can be available?
I can make slides available. Yeah, I'll post them on Slack. I'll post it after class today, and I'll try to do it before class going forward.
I'm assuming it's probably a yes, but like the expectation that we're going to be organizing a lot of out-of-class meetings with our teams to spend time together working on projects?
Yeah, it's kind of up to you how you want to do that. I think if you all live nearby each other and you want to just meet up after work, then I think that's a great way to do it. It's very possible to do it asynchronously as well. Great. So what are we going to cover for the rest of today? The first thing I'll do is just kind of, actually the project selection lecture. Okay, almost everyone. Almost everyone is at least not admitting that they didn't have a chance to watch it. Regardless, I'm going to quickly review it just to kind of catch the highlights and refresh your memory, and give you a chance to ask any questions you had about that material. Then I want to actually build on a couple of points that we covered in that lecture. One is, we kind of breezed over this question in that lecture of how to think about, what machine learning problems are easy and what machine learning problems are hard beyond data availability. What problems are hard to train models on. So I put together some thoughts on that, and we'll talk through that. And then also in that lecture, we skipped over how to think about setting up a code base. And so, with the remaining time, I'll walk you through kind of what a relatively mature machine learning code base looks like, so you can have some inspiration for how you want to set things up for your project. And then we'll talk about homework for next week, and then we have our guest speaker, Neil, at the end. All right, so to review, we covered a few things in this project, and the first or in this lecture rather, and the first was how to think about the life cycle of a machine learning project. And so to review, there's kind of a bunch of different steps that happen in any machine learning project that you're working on. The first is planning and project setup. So what are we going to work on at an abstract level, and then more specifically, like in a machine learning context, what metric are we actually going to be optimizing? Once you kind of have a plan for your project, then you go and collect a data set and you label it. And once you have a labeled data set, then you go and train a model and debug it. And once you're happy with the performance, you deploy it and you test it. And the key point here was that this is not actually a linear flow from beginning to end. What actually happens in practice is that people kind of move through these steps fluidly and loop back frequently. So for example, if you're collecting your data set and you realize, actually, it's kind of impossible to get labeled data for this problem, right? Then you might go back to project planning and say, okay, is there a different way of formulating this problem where it's easier for us to get labeled data? Similarly, if you're training your model and you just can't get the loss low enough, it just doesn't really seem to be possible to get a model to work well enough on this data set, then you might go back and look at your data collection process, and you might see if there's maybe some mislabeled data, or if there's some way of making that easier, or you might go back to project planning and say, what, this isn't going to work. And then finally, in the deployment stage, I think this is a really, really common point for things to loop back. In academic machine learning, you're typically given a data set and you train models over and over and over on that data set until your loss finally gets low enough, and then you're like, yes, and you publish the paper, and and you're done. It's really exciting. But in the real world, it doesn't work that way, right? Because in the real world, you have way more varied data than you can possibly collect a small data set to cover. And so what often happens is you deploy your model in production, or hopefully in some sandbox version of production, and then you realize hey, this isn't actually doing exactly what we want it to do. And so that's often when people will go back and figure out what the edge cases are, recollect data, or maybe add some other metric that they want to make sure that their model is optimizing. And so beyond the stuff that happens for every project, there's also kind of things that go into making a really good machine learning team. One of them is just kind of how do you find good people? How do you hire? How do you manage a machine learning team? And then the other is, what does infrastructure and tooling look like to be able to run a number of these projects successfully? And we'll talk about almost all of these things throughout the course of this class. Were there any questions on this concept, kind of how the life cycle of a machine learning project evolves? Okay, good. The next thing that we talked about was, you're in this planning phase, right? And so you're trying to figure out, we have this machine learning team, amazing machine learning engineers. What should we work on? What's going to be the highest impact thing that we can possibly find? This is a really hard problem, but there are a couple of mental models that we talked about that can be useful when you're thinking about this. One is the idea that, fundamentally, one of the things that machine learning really does is it allows you to create zero-cost predictions. So traditionally, if you want someone to predict something for you, if you want that person to be good, it's going to be expensive to ask them, okay, which way should I turn the steering wheel, or what is the economy going to do next year? But in machine learning, if you have a trained system, then that the marginal cost of producing additional predictions is 0. And so you can, one thing to think about is like within your organization, what are places where like free prediction essentially would make a big difference. And then the second, and this comes back to this software 2.0 idea, but where can you take, if the idea is that like gradient descent can write better code than you, right? So it's kind of tongue in cheek, like it actually, it can't write better code than you in most cases, but in some cases, like your optimization algorithm is going to find a much better way of, classifying images or translating text than you can possibly do with a rules-based system. And so thinking about parts of your software pipeline where you have like a bunch of handwritten rules, a bunch of heuristics, and then thinking about how you can automate them. Yeah, question in the back.
Where does stuff that was not possible before deep learning fit into this bucket? So something like auto reply, it's near impossible. It's not cheap, but it's near impossible to do it in manual software techniques.
Yeah, so how would you think about auto reply? I would say that like you could imagine auto reply before machine learning, right? You could say like maybe if Google's customers were high enough value, then they would totally just hire people to come up with suggested replies for you, right? But the problem is that like I'm not creating that much value for Google, so they're not willing to pay someone to to write my emails for me, unfortunately. But if it's free, then they might as well do that. Other questions about how to find high impact projects? I'm kind of expecting a lot of questions here because I feel like this is not comprehensive, right? Like there are a lot of projects that are high impact that are not covered by either of these things, and this is kind of vague in some sense, right? So like how do you all think about this? Yeah.
This is maybe answering a slightly different question, but when you're saying high impact ML projects, you're thinking of like very specific applied use cases. Do you have any sort of general advice if you're interested in like a more research flavored but still high impact project?
Yeah. So the question was how to think about this if you're interested in finding a project that's high impact, like in a business sense, but also is really interesting from a research sense. Is that? Yeah, I think the currency of like interesting research, most people would say is novelty. And so the thing I would look for there is like I would look at projects that you think could have a big impact to like that you can make a business. And then I would think about the ones where like you kind of know what the answer is already. Like, okay, we could, we kind of know how to do classification. We need to build a big data set, and then we need to train a model, like a ConfNet to classify things in those images. But if the application itself is sort of more like something that's really difficult, that's like less understood how you actually do that with machine learning, then that can be a good way of finding problems like that, I think. Yeah.
Where does cost figure into this?
Oh yeah, cost is on the next slide. Yeah, that's a good point though. Mm-hmm. Uh-huh.
Kind of like bridging the utility costs as well. Again, not a cheap thing, but the kind of advantage of zillions and zillions of hard-coded rules is that you know exactly what we do.
Yeah.
And you have a predicted outcome. It's not always the case with the machine learning. So usually the high-impact projects are the ones that are close to money, and it also means that the cost of high recall is really high.
Mm-hmm.
So how do you bridge that?
Yeah. So the question is, how do you bridge the fact that most high-impact machine learning projects are also going to be very expensive, essentially?
Expensive if you make the wrong prediction.
Expensive if you make the wrong prediction. Yeah. I mean, the way, like, just in general, the way I think about selecting project is, you want to think about like how impactful is this going to be? Meaning, like, if we're able to do this successfully, then what's the value that we're creating, and then what's the cost? And then you want to like pick projects that are low expected cost and high expected impact. So I I would try to balance those two things. Like if the project is extremely risky, then maybe you just don't do it. Yeah.
Just a comment actually. Do you think explainability is also considered a cost?
Mm-hmm. Yeah, so the question was, is explainability a cost? Yeah, so I think explainability is one thing that makes projects expensive because it's very difficult. Yeah, so I would consider this like something that ramps up the difficulty of the problem. And so, by doing that, it makes the project more expensive. And so let's actually use that as a segue to talk about costs. The way I think about like kind of how to figure out how expensive a machine learning project is going to be is, some cost drivers on the left from bottom to top in order of how important they are in terms of driving the costs. And I think that really the number one thing is data availability. And so this means both like how easy is it to collect data, how available is it, how expensive is it to collect, but then also how expensive is it to label. And this is super, super critical for a lot of applications because, for example, if you're working in medicine and you don't want random people on Amazon Turk making your medical decisions for you, then that means that you need to have doctors that are actually labeling your data for you. And so the labelers can actually turn out to be one of the most expensive parts about creating the data set. In addition to data availability, the accuracy requirement of your system is also a very big cost driver. And so there's a slide in kind of the main presentation that showed like kind of an exponentially growing curve. And the idea is that, like generally speaking, from what I've seen, project costs tend to grow faster than linearly in the sort of the number of nines that you need in your final accuracy, right? So like if you need your thing to be 99% accurate, and that changes, and now you need it to be 99.9% accurate, then like sort of like very, very rough rule of thumb is like maybe that project would be 10 times as expensive. So if for your application you need things to be super accurate, then the project is going to be very expensive. And in particular, the cost of wrong predictions is like a major driver of that, right? So self-driving cars have very expensive wrong predictions, and that's one of the reasons why it's been so expensive to develop them. And then the last thing is problem difficulty, and I think this generally seems to be less important than the other two things, but is also can be important. And I want to talk a little bit more about that in a few minutes. Questions on assessing costs of projects? Yeah.
Along with the one before, so one before was kind of how do you decide what projects you want to do?
Mm-hmm.
Maybe data availability being a big thing, you might decide what projects you can do with what you have at hand.
Totally.
How often, like, which direction do you find yourself starting projects from?
I almost always, for me, find myself starting from sort of impact, and then trying to assess whether it's feasible. But that's, I think, like driven by the context that I work in. I think from companies that I talk to, and I think this would also be a really interesting question to ask to Neil when he speaks later. But I think like oftentimes the impact question is like sort of part of your strategic planning, and then you start to build a data set, based on like data that you get from your users or that you're building to be an input to a system that's part of your product, and then from there, like the smaller projects that you decide to do within that context are largely driven by what data you already have available. Because if you're building like a massive data set from scratch, then that's just, it takes a long time and it's super expensive. Yeah.
Cost, like what's like usually the most surprising that comes up as you're doing this that you didn't think about?
Yeah.
Or like easy to get wrong?
Yeah, I think figuring out how much data you're going to need. Sorry? Yeah, the question is like, what's the most surprising thing that people get wrong? I think one thing that comes to mind is just like, how do you figure out how much data you're going to need for this problem, right? And so oftentimes you see like well, all right, we're going to budget for 100,000 labeled images for this problem because we read some paper and they used 100,000 images. But then what you realize is that like that paper only works in some really, really narrow circumstance. And so to solve the broader problem, maybe you need millions or tens of millions of labeled images or more. And so I think if you don't take that into account, then that's an easy way to get it wrong by quite a bit. Yeah.
Are the sizes of these problems roughly what you think is true in the real world? Is data availability a much bigger problem?
Yeah, so the question is, are the sizes of the parts of the pyramid representative? No, it's more just illustrative. Like I think data availability is like usually the biggest driver. If it's really, really hard to get data, then the project is going to be extremely expensive no matter what. Yeah, it's very problem dependent, right? Like for some problems, if some problems are like some projects can still be super expensive even if data is cheap because they're just research problems and you need to hire star researchers who are expensive and difficult to hire. So it's sort of a rule of thumb. Cool. So the next thing that we talked about was, once you have picked what problem to work on, you need to choose a metric. And so, in the real world, you care about a lot of different things. You care about your accuracy. You care about, how fast, like whether things run in real time, and like maybe many, many other things. But machine learning systems tend to work best when you're like trying to drive down one number at any given time. And the reason that this is important is because we saw an example of 3 different ways of combining precision and recall, and those 3 different ways of combining them could give you different scores for 3 different choices of model. And so if you want to pick which model performs best for your problem, you need some kind of canonical way at any given time of combining the metrics that you care about. And that way of combining them will evolve because oftentimes you don't really get it right the first time. But I think it's important at any given time to have like kind of alignment on your team about what's the number that we're trying to make go lower. Questions on metrics?
So do you see like how's the F-score used? Like F-score is also kind of combination of precision and recall. I've seen a lot of places F-score and beta score.
Yeah, so the question is about F-score, which is a way of combining precision and recall. There are a lot of ways of combining precision and recall. Depends on your problem.
But I've seen a lot of research papers about AP. They talk about AP a lot.
Yeah, mean average precision is another common way of combining precision and recall. Again, like the point of this is not really to make an argument for any one way of combining them over another. It's like the point of this is really there are many ways to combine them. Some of them are better in different circumstances than others, but it's important to kind of like when you start training models to have an idea of what metric you're going to use to evaluate them, so you can decide which hyperparameter choices and which model architectures are performing best in some canonical way. Yeah.
Just on this, like apart from this metrics really proves your model is good, but in real business scenario, like I saw like in the Tesla talk, like how they really validate from the systems. So like how do you think that real business scenario plays out? Like apart from the model metrics, have you seen some kind of calibrated values using real business systems and these models?
Yeah. So the question is, in a real business setting where you also have where you're also deploying this model, how does this play out? A couple of thoughts there. One is that one thing that a lot of people that I talk to do is they have their metric, their one canonical metric that they're trying to drive down, but then they also have a lot of other things that they care about, right? Like they care about whether their Twitter bot is going to say tweet racist stuff, right? So that's not the number that they're driving down, but if it did tweet racist stuff, that would be really bad. And so what you might do is you might actually create a separate test set or a separate validation set that captures this particular property of your model that you need it to have, and then just kind of threshold whatever your metric is on that. So you might say, I know that when my model reads these types of texts, I have 0% tolerance for it saying the wrong things on these examples, because these are just critical examples. So that's kind of one thing that you can do, still in the training and validation environment. One thing from the Tesla talk that I think is really cool, and I think more companies should be doing, is deploying their models kind of side by side with the production model and then keeping track of the predicted performance in a sandboxed way. So you have both models running in production, but the one that you already know works pretty well is actually making the decisions. But then the new one, sort of the prototype model, is there alongside it, and you're comparing the predictions, and then you can go back and analyze those and say, all right, for these 100 or thousands of miles of driving, how many mistakes did this model make? And then you can be more confident that in a production setting, the model is going to perform the way that you expect it to perform. All right. So in addition to choosing a metric, there's this other concept of a baseline. And what a baseline is it's some kind of measure of what performance you can expect your model to be able to achieve. So it's really like a lower bound on the expected performance of your model. And we talked a little bit about why this is important. So two different learning curves, two of the same learning curves, right? So our validation score and our training score, but different baselines, right? So different values for what human performance is. So on the left, if human performance is 36 or 37%, in that chart, our training error is kind of exactly hitting human performance. So, but our validation score is much higher. And so in that type of setting, we would say, well, we're actually overfitting to our training set. But in the scenario on the right, where human performance is close to 20%, our training error is actually very, very far off from what we might expect human performance to be. And so in this situation, we're overfitting. And the interventions that you would have for your model in those two scenarios are very different. So the same model but a different baseline implies different next steps. And so that's why it's important to pick a good baseline. And the better the performance of your baseline, the more useful it is for doing this type of thing. Yeah.
Wouldn't in some cases you want your model to actually be better than the human performance?
Yes. Yeah, exactly. So the question is, wouldn't you want your model to do better than human performance? In many cases, yes. So that's why this is a lower bound on the expected performance. This is more a tool when you're still in the regime of trying to hit human performance. Once you get past human performance, then your baseline might be your previous best model or something like that. Mm-hmm.
And I guess the other question would be, how do you get more data if let's say you're getting images labeled by somebody?
Yeah.
How do you get more data to get it to drive down better than human performance?
So sorry, I didn't understand the question. How do you get more data?
I mean, it's essentially if your label data is coming from humans, how do you get more data that gets your model to do better than humans?
I see. So how do you do better than, so if your labels are coming from humans, then how do you beat your labels? It's hard. One thing that can work is, oftentimes when people say they're doing better than humans, what they really mean is they're doing better than a single human. So you see this a lot in these medical papers is, the ground truth score that they get is an ensemble of humans. So they have 10 experts say, does this is the cancer in this image malignant or something like that, and then they take the average of those 10 experts, but then when they say they beat humans, that means that they beat a single average expert. There are a lot of different places to get baselines. These can kind of come from outside of the machine learning team. So engineering team might say we need this to run in this specific kind of latency to run in real time, or you can look at papers to get that. But oftentimes the best thing to do is actually build your own baseline. And so that can be human performance. It can also just be a simple linear regression model, or it can also be a scripted baseline, something like an OpenCV script. And I'll just tell you a little story about that. I can't remember if I told this in the lecture or not, but I did. Okay, I'll skip it then. But the story is basically the first month or so of the Dota project, the best engineer on the team basically spent the entire time not doing any machine learning training at all, just trying to build a really, really good scripted Dota bot that can, because the built-in bots in the game were pretty bad. And so he ended up, over the course of a month, building the best Dota bot in history at that point, actually. But the machine learning bot beat it within another month of that. So, but it just, I think, illustrates the importance of of having a good baseline that, that he invested that time in building that bot. Okay, yeah, so to summarize, when you're planning and choosing a project, there's a few different steps that you follow. You first figure out what the goals of that project are. You pick a project. Then you choose what metric you're going to optimize, at least initially on the project. And then you pick some baseline and you evaluate it to get a sense of what performance you can expect to try to beat. And then finally, you have to set up your code base. And I'll go into a little bit more detail on code base setup in a few minutes. All right, any other questions on this lecture? Yeah. Mm-hmm.
So, I think maybe it's a naive question, but how is the code base set up after evaluating and choosing metrics?
So the question is, how is the code base set up after evaluating and choosing metrics? Usually, like when I say choosing metrics, it's kind of like looking at your problem and saying, okay, is this a place where we use mean average error or mean squared error? And so you can often just kind of do that by thinking about it. And also often you'll have some sort of hacky scripts that you can use to start training things before you really invest in a code base that a lot of people can work together on. Yeah?
For the Dota story, how did you justify that 2 months for building the best bot versus taking whatever was the best at that point?
Yeah, I think, so the question is, how do you justify spending the time on building a bot? I think they just kind of felt like the bots that were built into Dota were so pitiful that they didn't feel like if they beat them, that would really be indicative of any sort of performance. And so they wanted something where they know if you beat it, then your model's learning something intelligent.
So when you
Yeah.
say baseline, you really mean a really good system, not a naive system. Then, right? Like when you say these baselines, this is like one human expert predicting it.
Yeah, I would say, like almost everything else in machine learning, it can be iterative. So maybe when you first start on your project, you just use a linear regression. But the better the performance of your baseline, the more useful it is to you. Because if the performance, you get a baseline that has better performance, then that means that that means that there's a bigger gap between your model and what you can expect it to do. And so that gives you a better sense of how well you can expect your model to do. Yeah.
I guess as a practical matter, the timeline for the class
Mm-hmm.
is, it seems like maybe there's 1 or 2 weeks to build a baseline.
Mm-hmm.
And that seems like, I don't know, that just seems like a really short time, and I'm wondering how that, might constrain the choice of projects.
Yeah.
You spent a long time, trying to build your baseline.
Totally. Yeah, it is. The question is about the timeline of the projects. It is a very tight timeline, but I think it's more than enough time to kind of to build a cool machine learning project. And yeah, I think it does. I think it very much should influence the choice of projects that you make. And so one thing that we'll ask you to do, not this week but next week, is to put together a project proposal, and then I'll kind of give you feedback on whether it seems like it's feasible to achieve within the time frame. Mm-hmm.
I've seen software they say you choose the baseline how it will do if you just do randomly, or the 50% in a raw case.
Yeah.
The baseline. Or you're talking about SRE, something like a Bayesian error where they talk which one you choose. One is at the low end, the other one is fairly high.
Yeah. So is the question? Sometimes people choose randomly as a baseline, and why would you do that as opposed to something like regression?
Bayesian error, which is the best, you can't really beat that.
Mm-hmm.
Like the high-end baseline and the low-end baseline.
Yeah, I think so. Sometimes these really naive baselines are the best you can get, and sometimes if you have bugs in your machine learning system, you won't even beat them. So I remember actually one time spending a really long time trying to figure out why my model wasn't performing that well, and then I compared it to the average of the outputs of the model, and I actually wasn't beating that. So I was very confident that I had a bug after that. All right, the next thing I want to talk about is how to think about what types of machine learning problems are easy and hard. So the first thing to say here is, there's a long and illustrious history of people getting this very, very wrong. So this is a quote from the New York Times about how long it was going to take humans to beat the best players in Go. Right. So this is right after Deep Blue. So right after AI beat humans in chess. Contrast that with this headline from less than 20 years later about DeepMind actually finally beating the best humans in Go. Right. And so this is like one of many, many examples of how difficult it is to figure out what what AI problems in general are difficult. And so all of this is said with that in mind, that like this is all just a guess. But I think that we can confidently say that there are some things that are still hard to do in production right now in machine learning. And so a couple of those things are anything that's not supervised learning. So unsupervised learning, reinforcement learning. Both of these things are extremely promising research directions, and there are a couple of use cases for them in production right now. But generally speaking, they're showing promise in kind of more limited domains and places where you have a ton of data available. So I would say, as a rule of thumb, applications of unsupervised learning and reinforcement learning, with a couple of exceptions, are sort of not quite ready for prime time yet. But what about within supervised learning? Actually, I want to crowdsource this. So can anyone think of examples of problems where it's a supervised learning problem, but we still machines still can't perform very well on them? It's like, let's say that we still can't do nearly as well as humans. Yeah. Document summarization. Yep, that's a great one. Yeah. Can you be more specific? Yeah, detection of diseases from lab results and X-rays. Yeah, I mean, there are some specific medical applications where people now are claiming that AI does better than doctors. Most of those are things like radiology, where they're just kind of inferring something from an image. But the more general problem of looking at all of someone's clinical data and determining what disease they have or what action should be taken is very much unsolved still. Yeah. Grasping objects. Yeah, this is a great one. Because I spent a lot of time working on this in my PhD. This is actually really surprising to me when I started working in robotics. One of the really surprising things about robotics is that you can all of the questions that a 5-year-old can ask are still and can solve are still unsolved. It's one of the fun things about working in robotics. Yeah, sure. If anything requires a lot of data, then it's still very difficult. Yeah. Mm-hmm.
I think that depends on the data and the problem. So any kind of interpolation questions. So your data kind of covers the domain of the problem that you're trying to solve, then supervised learning works well. But if you have to start extrapolating,
yeah,
or your data has cannot describe or cover all the domains that you have to cover, then the problem becomes pretty hard.
Yeah, I think that's right. So the idea was anytime you need to extrapolate from your data, so you need to answer some question that's not kind of explicitly present in your data. Generally, supervised learning does not work for those things. I'll list some things that I came up with. Answering questions is still very hard. Summarizing text was mentioned. Predicting video. So you see some sequences of video frame and you need to decide what the next one is going to look like. Building 3D models of the world. This one I think is pretty surprising actually, but actually traditional computer vision is still better than deep learning at understanding 3D structure of the environment. Speech recognition in the real world. There's a lot of amazing kind of academic results in speech recognition, but understanding doing voice to text in crowded environments over the phone and things like that are still extremely difficult. Resisting adversarial examples. How many are familiar with adversarial examples? Okay, most are familiar. Adversarial examples, essentially the idea is you can take an image classifier that does really, really well, and then you can create an image that looks identical to us, but completely fools the classifier. And there's a very simple procedure to do that involves just kind of back propagating the error from that image and adjusting the pixel values of the image by some extremely small value. And so when you look at it as a human, it looks exactly the same, but for some reason, the machine is confused by it. And so this is kind of a challenging thing for like if you think that, if you're worried about people kind of hacking deep learning systems in the real world. Doing math, which is funny, right? Computers are great at math, but like there are a lot of really interesting results of people training recurrent neural networks to add numbers and then seeing that they don't generalize even when you just add a couple more digits to the end of it. Solving word puzzles, like kind of the type that you might have seen in lower school or middle school. Bongard problems, I'll show you what those are. This is kind of like visual analogy problems, visual reasoning problems. So you have shapes on two different sizes, or on two sides, and the goal is to kind of see what facet of the shapes is different between the examples on one side or the other. So the ones on the right are the ones on the left are convex, and the ones on the right are not. This is still not solvable by neural nets. Okay, so let's try to categorize these and understand a little bit about what makes these problems more difficult than things that we do know how to do well. So I think the way I think about it is that there are a few different types of problems that tend to be really hard. The first is if the output itself is very complex. So it could be high dimensional, like in 3D reconstruction, or in video prediction, or it could be ambiguous, right? Like if there's many different possible outputs, like in dialogue systems or also in video prediction, then that also makes things very difficult. I think also if reliability is required of the system, and reliability can mean different things. It can mean robustness, like robustness to adversarial examples, and it can also mean high precision. And so one thing that we have found very challenging at OpenAI that has been very surprising to us has been that to create a very accurate, to create a model that estimates the pose of an object, so like kind of the position and rotation of the object in the 3D world is very easy. But then once you try to start getting that pose estimation down below some threshold, it starts to become very, very hard. Because neural networks tend not to do very well at things that require a lot of precision. They're much better at things like classification, where you're just getting a coarse answer from the network. And then anything I think where generalization is required. So if you're, if the data that you're ultimately going to evaluate on looks different than the data that you're training on, you generally speaking have no guarantees that your model is going to do anything reasonable whatsoever, right? Like much less be good, but like it could be kind of wildly wrong. And then also in this category, I'd put anything that kind of feels like reasoning or planning or understanding causality. These things are still very difficult to do. Yeah.
What you said about reliability made me think of a question. So I don't know what the state of the art is, but how are neural networks at estimating their own confidence in a result? Do they do that well?
Yeah, so there's a lot of research going to this, into understanding how neural networks understand their own confidence. Generally speaking, I would say that neural networks are extremely bad at understanding their own confidence. And so there's kind of like an interesting paper that illustrates this, which it takes MNIST, which is kind of like the classic computer vision data set, a bunch of digits. And then it takes another data set called omniglot. And omniglot is handwritten digits from like foreign languages. So they're like kind of different. They all kind of look like MNIST images, but the digits themselves are different. They're not 0 through 9. And so what they did in this paper is they showed that if you train a model on MNIST that does really well on MNIST, and then you feed it some data from omniglot, you can find examples where the model makes extremely confident wrong predictions. So it sees some digit that doesn't look anything like us to a 0 through 9, but the model will say 95% accuracy, that 95% confidence that this is a 2 or something like that. Yeah.
That research, was the classification like you had only 10 classes, or was it like CPC where you had this strange class?
I think in that particular paper, if I remember correctly, they did not have like a strange class. They just did 0 through 9, but then confidence, you can still get confidence by looking at the weights of the softmax. So like what you'd expect to happen is the model would produce equal probability on all of them. And I think follow-up papers, they've explored the idea that you're talking about. Okay, questions, thoughts on this? Other counterexamples to this? Things that are hard that this doesn't capture? Okay, yeah, I just wanted to give you a little bit of a flavor of, to build a little bit of intuition about, if you're thinking about some problem, how to get a sense of, beyond just going and reading papers, whether this is something that's should be feasible for machine learning to do or not. All right, and the last thing that I want to do today is just kind of start to walk you through what a mature machine learning code base looks like. And then I'll ask you to kind of like spend more time looking at it on your own. But so first, just to give you a sense of what this code base is doing, this was kind of the class project for one of the boot camps that we did. And so the goal of the project is, you have like an app, and what you do on the app is you take a picture of some handwritten text, and then the goal is to then produce the the typed version of the text that that the user input. And so the way the system that we built works is, first there's a web backend that takes kind of the raw data from this app, decodes it into a format that the neural network can understand, and then sends it to a prediction model. So this is like kind of, you can think about this as like the weights of a neural network. And that it's not super important like the details of that model structure, but it's actually in two separate modules. And then that's kind of sent back to the web backend and produces the final result. But that's kind of not all of the parts of the code base. You also need to figure out how to produce the weights of this model, like what weights of the neural net actually produce the best loss. And so there's also a bunch of code for training models. So there's data sets and there's training code, and those produce kind of the final model weights. Also just want to quickly mention a couple of best practices for like at a high level how to think about machine learning code-based design. And this is not really all that different than just general code-based design in software engineering. Modularity is really important. In machine learning context, what this typically means is that you have separate code for data sets, models, optimizers, loss functions, things like that. And you want to set up your code base in a way that you can mix and match between them. So like a lot of times what I see kind of with people that are less experienced software engineers that are building machine learning code bases is that they, the model that they build depends really heavily on assumptions from the specific data set that they're using at this time. And the problem with that is like oftentimes you need to change what data set you're using, or you want to just reuse the code that you've already written for training on some different problem where you have some data set that looks kind of different. And so a lot of the design choices that we made in the code base that I'll show you in a second are meant to have modularity for those types of things. Another kind of best practice that I've heard from a lot of people is having a self-contained prediction module. So having kind of like a folder within your directory that has just the minimum set of things that you need in order to actually serve predictions to the user. So it might be like the raw weights of the model and the logic for interacting with the raw data, and then a very thin wrapper around those weights that tell you how to turn those weights and the data into raw predictions. And so the idea is like this is just something that should be super easy to deploy and doesn't have to deal with the complexity of all of your training code. And then one other thing I'll mention I think is that I think is important is like usually what I see is people manage their data separately from the way that they do version code in their control. But oftentimes like what is checked into into Git is like some sort of logic for getting the data. So you might have your data stored in on S3 or some other sort of data storage, and then like within your code base on Git, you might have some rules for like the specific version of the data set that you're using, how to actually go and download that from S3. All right. Actually, any questions about this? Yeah, is there a reference for a good project? I'll show you one that I think is pretty good in a second. Yeah.
You didn't talk about model versioning in this thing. You talk about code versioning, data management. You also keep track of model performance and versions.
Yeah. So keeping track of model performance and versions. I swear this is not a plant, but I actually use weights and biases for this, and I think it's really great. Yeah, I would encourage you all to at least try using it as well. Yeah.
Could you talk maybe about the infrastructure that you've seen work before? And once you deploy a model, a problem that everyone had is how do you see when it starts drifting or when it starts, maybe not performing so well?
Mm-hmm.
And have you seen any particular paradigms that work well for that?
Yeah. So how do you deal with once you have a deployed model, you might have some data drift, and how do you catch that early? I think the way to do that is by trying to capture some of that drift with tests, and then the idea is to try to capture it as early as possible and flag it. And there are a couple of different causes, like potential causes. One is data drift, but another is some sort of regression in your code base. Like you train some model and it looks like the model is performing really well, but in reality, it doesn't perform as well in the real data, and so you need to kind of quickly be able to go and revert that back. We'll talk about this in more detail second to last week. Yeah.
When data is managed separately from code, usually that's the evolution of the code that informs you that data needs this new revision. Like you had a better architecture, and now you need probably better data or more data. That won't be a version of code. So how do you keep track of two versions?
Yeah, how do you keep track of, so you have version control for your code, and then you have, and what I'm saying is you want to manage your data separately from that, and those two things interact. So the question is, how do you manage that interaction? I think one way to do this, this is something that I've seen in practice. I'm not sure if this is, there might be a better way, is to sort of pin your your training code and your model code to a specific version of the data, and then you can be conscious about how you update that. So it's kind of like if you have to manage some unstable dependency in your code base. All right. I want to quickly just kind of take you on a very, very brief tour of this code base, and then I'm going to encourage you all to spend time looking at this on your own. But if you have your computers, you can follow along. This is the URL. Okay, so what you're looking at is the code for the labs for this bootcamp that we ran a month or so ago. And if you go to this URL on your own, I would encourage you to kind of poke through each of the labs and maybe try some of the exercises and just kind of get a feel for it. But right now I'm looking at the solutions for lab 9, because this is kind of shows the code base in its most mature form. So a few things to notice here. The first is that we have this API folder. And this is kind of like the minimal version of serving the model that I talked about. And so it contains a Docker file for those of you that use Docker to kind of specify what the dependencies are for the production version of the model. And then it contains kind of an app, which is the logic for how you serve predictions from the model. And then some other specifications for how to make this run. And the weights, when you deploy your model, the weights are actually just copied into this folder. Then there's kind of a couple of folders that are just more for convenience. So there's notebooks. A lot of times, Jupyter notebooks are really good ways of playing around with your data, testing out your models and just kind of seeing in an informal way how they work. And then tasks. These are just convenience scripts for doing things that you are going to do frequently in your code base. So things like running your tests, training your models, and linting to make sure that your code meets code standards. And then the meat of this folder is this project is in training. It's in text recognizer. And so this is where we have most of the code for kind of how you build models and how you build loss functions and neural networks, and then how they interact with optimizers. So there's data sets. And so this is not actually where the raw data is contained, but this contains the logic for how to turn the raw data into something that's consumable by the model. Then there's models and networks. And the distinction here is that I think of a network as sort of like a dumb input-output mapping. So a network is, f of x equals y. And then a model contains all of the other stuff that you need in order to use that network and train it. So it contains things like how you define the optimizer for that model, what does it mean to take a gradient step on that model, how do you turn sort of the raw output into the actual structured prediction and things like that. And so the reason that there's this split is because if you just have networks, then you can kind of really easily change your neural network architecture without having to fuddle with how that interacts with the rest of your code base. So it sort of isolates that. And then we have tests and a folder here for storing the best current weights. All right, so that's just a very, very brief tour of what this code base looks like. And the next thing I want to talk about is your homework, which part of that will be looking through this code base in more detail. All right, so again, each week we're going to have you watch one of the lectures. And so for next week, we'll have you watch the data management lecture. And you don't need to write this down. We'll kind of post all this stuff to Slack as well. But that's the link on YouTube. And then, I didn't really have time to go through the text recognizer code base in a lot of detail. And so I want you all to start getting familiar with this so that you have a sense of kind of what a really good sort of production-ready machine learning code base looks like. So I want you all to read through it and then kind of take your choice which of the following assignments you want to do. You can do one of the labs if you want. Most of them involve filling in code to kind of specify the way that you do the neural net or the way that you serve predictions. Or you can post a question about it on Slack. So find something in the code base that you're not sure about, like why did we structure it this way, or why aren't we doing this thing, and post that. Or, and this is highly, highly encouraged, you submit a pull request to this code base, you'll get extra credit in the meaningless point system of the course. But I think this is the best way to learn your way around it. And so I'm not expecting everyone to do this, but I hope a few of you choose to do it. All right, but kind of more importantly than these is to start working on your projects. And the first step here is we want you all to pick your projects. And we have a specific way that we're going to do that. So we've set up I can't find my mouse. There we go. We've set up an Excel or a Google Sheet that has a bunch of, it's pre-populated with a bunch of suggested project ideas. And so each of these project ideas kind of has a very brief description and sort of a very rough estimate of how hard they're going to be, both in terms of how hard they're going to be to build a good labeled data set and also how hard they're going to be to find a good model to train on them. And then what we have over here is columns for people. So there's a maximum of 4 people for the project. And so what we want all of you to do is to start going through these projects. And when you kind of have a sense of what project you want to work on, add yourself to one of these columns for that project. One other thing I want to say on this, the projects I put in here are kind of just projects that I think would be fun to do, but what I really want people to do is to come up with their own projects. So if you have ideas for a cool side project that you want to work on and want to get people's help with, then I would highly encourage you to add them to this sheet and maybe lobby in Slack a little bit to convince other people in the class that your project is the most exciting one to work on. Yeah?
These projects have data available?
Sorry?
The project that you have mentioned, do they have the data available, or is that also?
Yeah, so the question was, is the data available for the projects that I suggested? It's a mix. So for the ones where I said data availability is a 2, generally what I meant by that is there's some publicly available data set that will get you most of the way there. And for the ones that I said were a 4 or a 5, generally that means that part of what you're going to have to do for this project is to build the data set yourself. Building data sets is challenging. And if you choose one of those projects, I'd highly suggest getting started on that very early. But oftentimes those can be the most rewarding projects because if you're working with some publicly available data set, then chances are a lot of people have tried things on that data set before. So it's up to you. I leave it up to you, how much effort you want to put into building your own data set. Yeah?
Do you have objectives on what should be the goal of a project?
So what I'm hoping for these projects is that at the end of the course, so 7 weeks from now, each team, so each 1 or 2 or 3 or 4 of you have something that you can showcase that demonstrates that you've built like a prototype of a machine learning system end to end. So like I'm not expecting you to go and and like solve some problem and sell your system to Google for $100 million. Because if you can do that in 6 weeks, then then you can teach the next version of the course. It's like going to be very difficult to completely solve a problem in this time frame. But what I'm hoping is that we'll have really cool demos that kind of show that you have a system that like is starting to work in the real world. Yeah.
So one of the steps in proposing a new project idea, right, would be like to fill in, okay, here's a description of the project, but then also to estimate the difficulty.
Yeah.
And I'm curious if you have sort of just a process for vetting, our estimates. I would just be guessing. Right,
yeah.
Before people sign up, or we just kind of like try it and then we turn it wrong.
Yeah, totally.
How does that fit into the selection process?
Yeah, so when you're putting your projects in, yeah, you should just guess at the difficulty. I mean, you should use the tools that that we talked about in this class to guess the difficulty. And like to be clear, the difficulties that I have here were like my guess that I did this morning. So those are also like very much subject to be wrong. But if you put like some guess for difficulty that's like wildly incorrect, just know that I'm going to be stocking the sheet and calling you out for it. So yeah, that's the accountability mechanism. Yeah.
With the goal of the end-to-end project in mind, does it make more sense to pick projects that have no difficulties on both those columns in order to focus on best practices of code and other aspects of it?
Yeah, I kind of want to leave this up to you. I think I think if you're sort of newer to machine learning and you haven't like built a project on your own before, then I would recommend choosing something where you kind of know where you're going to get the data from already, and you have a good sense that you can find a model that's going to work for this data, and then just like focus on getting one thing working end to end. If you're sort of more experienced, like some of you kind of have been like working as machine learning engineers for quite some time already, then challenge yourself and like use your best judgment. Yeah.
So maybe a little late, I had a question about the pull request, whether you had any sort of guidelines as to what we should aim to. Because that'd be cool to do, but what kind of pull request are you looking for?
Yeah, submit a pull request that I will be excited to merge. Yeah. No, I think there's like, this code base is not actually used in production. We built it as an example of a sort of like a simplified example of a production system. And so there are a lot of things that that we just didn't really have time to get working the right way. And so, as you poke around the code, you will find those. And yeah. Mm-hmm. So for the demo, I think it depends a little bit on what your data set looks like. Yeah. What's the question? Yeah, I mean, so the goal is like, if your thing is like an app, like to have, you don't need to build like an iOS app, but to have some sort of, web endpoint that you can like, so you can pull out your phone and show it to your friends. Yeah.
Couple of questions. So when it comes to these projects, right, many a times when you are trying to do an end-to-end solution, it might be much easier to use multiple languages, multiple different types of scripting and coding. Is that an acceptable thing, or do you expect it to be done in one particular language, like Python?
So the question is there a language expectation for this? I'm going to strongly encourage people to use Keras. And we'll talk more about this next week. I just kind of think it's like the best way to get things to actually work. If you have a problem where Keras doesn't make sense, then then let me know why, and there like definitely other languages that could make sense for certain projects. Yeah, I'll take this as the last question, and then we're going to move on.
This is kind of like a side question.
Yeah.
From your experience, what are the problems which deep learning does worse than classical machine learning?
What are the problems where deep learning does worse than classical machine learning? A few things come to mind. One is just anywhere where you don't have a lot of data. So if you're in a domain that has limited data, classical machine learning tends to do better, tends to generalize better. Another thing that comes to mind is causal reasoning. So there's sort of like a whole literature around causal reasoning in classical ML that doesn't work all that well, but it works better than sort of the non-existent causal reasoning in deep learning. And then the only other thing that really comes to mind is sort of geometric understanding, like understanding of 3D structure. And this is actually really surprising to me. I don't think it should be true, but as far as I can tell, for things like 3D reconstruction, classical pipelines still tend to work better, maybe with a little bit of deep learning sprinkled in. Great. That's all for me. Next up, we have our guest speaker, Neil Khosla. Neil is, I would describe Neil as sort of the rare entrepreneur that is crazy enough not only to start a machine learning startup and not only to do it in healthcare, but actually to do two at the same time. And so Neil, I think, like I've always been super impressed by Neil's insight about how to think about sort of like what machine learning problems or just what problems in general will be really impactful for people to be working on. And so I'm really excited to have him here. Cool. Thanks, welcome.